Today we're going to be talking about scientific notation. And what is scientific notation? Well, scientific notation is a shorthand form that scientists in particular use all the time in order to express either exceptionally small or exceptionally large numbers in a very short form. So oftentimes you might notice on your calculator, then rather than it writing, let's say 7 billion, which is the number I just wrote here, what it will instead write is it'll note that this decimal place has to move 1, 2, 3, 4, 5, 6, 7, 8, 9 places over to the left here. So it'll instead write 7 times 10 to the 9th power, aka your calculator will write 7e6, which that means 7 times 10 to the 9th, because after a while your calculator just starts to run out of room. That's really the use of scientific notation. Or when you're reading scientific literature, people get overwhelmed by the sheer number of zeros, and by writing something like 7 times 10 to the 9th, you very quickly communicate, hey, this number is in the billions, and this is how much it's in the billions, without having to get lost in the sauce of all the details. So how do you recognize something is in scientific notation? So just by convention, the way that scientific notation works is you're going to have some leading coefficient times 10 to some integer power. This n is going to always be an integer, and it'll be positive if the number is large, because that's how many times you're multiplying it by 10. That's how many place values deeper you're getting. Versus it'll be negative if the number is small, because remember, multiplying by a negative exponent ends up multiplying him by a fraction. So for example, for this number that we have here of 4.53 times 10 to the negative third, remember that 10 to the negative third would be rewritten as 1 over 10 to the third power, because negative exponents end up going into that denominator and then becoming positive, which in particular is 1 over 1,000 that you're really multiplying him by, because 10 to the first is just 10, 10 to the second is 100, 10 to the third is 1,000. So you're basically doing, in this case, 4.53 divided by 1,000. So you're dividing 4.53 into 1,000 pieces, which is how you end up with 453 thousandths being the number that you're actually expressing, because remember, this is the thousandths place that you have right there. And in general, that's kind of what you always want to be looking for if you're identifying, is this number in scientific notation or not? You want to be making sure that leading coefficient is a number between 1 and 10, not inclusive on the 10, because as soon as you hit 10 again, you're going to want to multiply it by another additional 10 in the exponent itself, and then you can't include the 1. You don't want to be less than 1, because that tells you, hey, we should really actually move this over yet another place value. So go ahead and pause your video and check yourself for some understanding which of these numbers are in scientific notation. So if we're checking ourselves here, let's actually do this in blue. This first one is in scientific notation because in particular the coefficient is between 1 and 10, and this exponent is an integer, so we're good to go. The second one is also scientific notation because the coefficient in terms of absolute value is in between 1 and 10, and then the exponent is also an integer. Third one, same deal. So even though this 10 doesn't have the 1 written, that 1 is implied. We just tend not to write to the first power. And the coefficient is again between 1 and 10, so we're good. The next three all have some sort of issue with it. In particular, this first one has the issue that that coefficient is not between 1 and 10. It's too small. So in particular, as we essentially moved over the decimal place too many places when we were trying to convert it to scientific notation, we will really want to move it an additional 1 to the right. So this would be equivalent to 3.04, but instead of being multiplied by 10 to the 22nd, it would be multiplied by 10 to the 21st, because we again kind of want to undo that additional place value that was making it initially smaller. So we want to undo making it smaller, make it a little bit bigger again in terms of that first number, so it would actually be times 10 to the 21st instead. For the second one, same sort of deal. There's a similar sort of mistake, so that coefficient is incorrect. You really want to move that decimal place over one more to the left. When you're wanting to move it over one more to the left, you're now wanting to add on an additional part of that kind of bigness, so to speak, to the exponent itself. So that would actually be 1.58 times 10 to the negative 23rd. So you're adding on an additional 1 to the exponent itself. And then this last one has, so for both of those, the issue was the coefficient. That was really the main issue. That the coefficient was, in the first case, made too small, and in the second case, made too big. So we want to undo making it too small by subtracting a number from the exponent, and then with the second one, we want to undo making it too big by adding a number to the exponent. And then for the last one, the issue is actually the exponent itself is not an integer. And to be honest, I don't know off the top of my head how to fix that exponent itself not being an integer. I think that this would just be a more difficult number to suddenly make into scientific notation. But so all three of those are not in scientific notation for those reasons. So now let's actually talk about converting to scientific notation, which we touched on a little bit up here, but now let's be a little bit more precise about it. So we want to move the decimal point for the first factor so that our number remaining is greater than or equal to 1, but less than 10, again, in absolute value. Then we want to count the number of decimal places that we have moved. And then we want to kind of just to make sure that we're sort of doing a big understanding sanity check. If the number itself is bigger than 1, that number will be multiplied by 10 to a positive power. If the number itself is less than 1 in absolute value, then that number will be multiplied by 10 to a negative power. So I would actually know this more so than trying to memorize, did I move to the left or did I move to the right? That's going to be less useful than just knowing, did my number get bigger or did it get smaller? So let's actually kind of dive into this a little bit more. So for this first one, we've got to move 1, 2, 3, 4 places. So it'd be 6.12 times 10 to the negative 4, because again, it's actually a negative exponent at the end of the day that we're dealing with, because the number itself is in between 0 and 1 in absolute value. Go ahead and check if you can do these next three yourself, and then we'll go over it together. So for the next one, we're moving over 1, 2, 3, 4, 5, 6, 7 places. So 5.678 times 10 to the negative 7. Because again, we actually became smaller, and I'm going to write that negative 7 a little bit clearer this time. For the next one, we're moving in the other direction. So we actually want to make a big number. We're going to move 1, 2, 3, 4 places. 1.0872 times 10 to the positive 4 this time, because we're making the number bigger. For the next one, we'd be moving over 1, 2, 3, 4, 5, 6, 7 places. So we'd have 3.562457 times 10 to, I think it said 7 places there, because we're again making the number bigger. And that 7 already tells you that we are going to be in the 10 millions, for example. The other 4 already tells you that we're going to be in the 10,000ths as another example. So this tells you kind of which place value you're in just from the exponent on that 10. So now let's talk a little bit about converting the other way around. And apologies for that very abrupt cut there. I realized that I had missing decimal places in the first draft of this document. So I went back and fixed that. And now we should be able to talk about working the other way around. So if you're going to work the other way around, it's going to be very, very similar to working forwards. It's just that you are instead going to actually move the decimal place and then record what the regular number is rather than the scientific notation number. And by regular, I mean standard form number. So if, for example, you have 2 times 10 to the negative 5th, well, you should be thinking right now this is the same thing as 2.0. And you can also sort of envision there are as many zeros in front of the 2 as you so desire. For 10 to the negative 5th, you should be thinking, okay, this number is getting smaller, which is why when it's a negative exponent, you end up moving the decimal to the left. So in this case, 1, 2, 3, 4, 5 places to end up with the number 0.00002 as your final answer. Go ahead and see if you can do these next 3 yourself, and then we'll compare together. So for the next 3, similarly for 2.98, and again, you can stick a few zeros in front to sort of help you visualize. You would move him over 1, 2, 3 places. So you would end up with 0.00298. And you should always do a quick sanity check that if it's a negative exponent, the number should be getting smaller, while if it's a positive exponent, the number should be getting bigger. Similarly, if you have 1.13290, and then I'm just going to add in a 0.0000, because that doesn't change the value of the problem. Although the decimal point's already there, so we're just adding in, again, more zeros there at the end, because it's already beyond decimal point, right? We don't have to add on an extra 1, but, if you have 1.00, that's the same thing as just 1. That's all we're noting. Now he's getting bigger, so we're going to end up moving the decimal point to the right. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 for the final location of the decimal place. So we're going to end up with, we've got a 1, 1, 3, 2, 9, 1, 2, 3, 4, 5, 6, 7 zeros. Let's see. So it looks like here that this would be 113, let's see, so that's the hundreds, thousands, millions, billions. So this is 113 billion is the normal number, which, this is a very good example of where scientific notation allows you to talk about this number much more succinctly, which is why we would end up normally using scientific notation for such a number. And then similarly for the last one, I'm going to envision a whole bunch of zeros out front because I can notice already that the number is getting smaller because he's being taken to a negative exponent. So move over 1, 2, 3, 4, 5, 6, 7, 8, 9 places for a final answer of, and I'm just going to draw that. Here we go. This very, very tiny number. So in short, what you want to do is move the decimal places, the number that is in the exponent, and you want to be making the number smaller by moving it over to the left if it is a negative exponent, or make it bigger by moving the exponent to the right if it is a positive exponent.